Okay, so welcome in. It's the second talk of the session. It's Tour of America's Dairyland, the barrier fastener team. So about 22 minutes. Thank you, Nick. Take it away, gents.
Hey, hello. We are the CHJ engineering group with our, like Dr. Hart mentioned, Tour of America's Dairyland barrier fastener solution. CHJ standing for Colin, Hoyt, and Jason. So in this presentation, we'll just run through some quick team introductions. We'll go over the project background. We'll cover the problem statement. We'll lightly touch on some of the research that we did to develop our solution. We'll touch on the specifications that we developed, our concept generation, the proposed solutions that we're coming with, and then the next steps and future testing that will be conducted next term. So for team introductions,
I am Colin Bergerud. I am a board member of the Raider 3D Printing Club.
I'm Hoyt Leitsky. I am a board member of the hybrid team.
I'm Jason Graham, president of 3D Printing Club. All right, so starting with our project background, Tour of American Dairylands is a multi-day road racing series held annually in the southwest of Wisconsin. They run about 11 to 12 races per season over the span of 11 to 12 days, depending on what it is. All right. And here we have a map of where all the races lie, or at least 2021. The races go through the streets and neighborhoods of Wisconsin, and they use the fences to signify where the racers will be going and where onlookers can be. As far as safety is concerned, currently the race is held by the fences. We have video to show what a crash looks like.
And so pay attention to the right side here.
Let's go into our problem statement. Like Jason mentioned, there is an issue with the fences. Currently, they are supported only at the base with this roughly foot-long flat plate with two tubes welded to the top of it. And the fences just kind of stick into those two tubes and can rotate as necessary. Many of the fences over time have been corroded, and that is an issue. And also the edges are exposed due to unevenness in the ground and so forth. So boiled down to a very simple statement, the misalignment of these fences causes safety concerns for racers. And it's not only the misalignment, but it's also the corrosion, which could cause damage to bikes and also injuries to people, and maybe cause health issues.
So getting into some of the background research that we did before developing any solutions. Before starting, it was cool over the summer, before senior design really started, we were able to attend one of these races in, I believe, Shorewood, and see firsthand how all these fences were set up. Most all the photos that you see in this presentation were taken by us at a race. So cool first person voice of customer. But as you can see, when racing, the bikers were very minimal protection. So they have their helmet, of course, maybe some glasses to protect, but really nothing on their body. They have very thin uniforms on to be as lightweight and aerodynamic as possible. So if they're running into one of these barriers, as you saw those exposed edges, there's really no padding, no thick clothing protecting them from those sharp edges. So that's really the problem that we're trying to mitigate. Early on, some crash mechanics were researched. So we knew that we were going to be dealing with crashes, so we started with crash mechanics. We weren't able to find anything in the way of existing research as it pertains to bicycle crashes and fences. There's not much done in terms of that field, but there is a lot of research with bicycle crashes and automobiles. So we were able to take that information and take the useful bits out of it and use the useful equations and models later on when doing dynamic and static simulations. So that was good. As a baseline starting point, not used later for like any factors of safety or anything, but we just did an initial impact force calculation. We just assumed, let's say bikers are 30 miles an hour. That's about average for these races. Can go faster, can go slower. Biker and biker weight is a pretty conservative 250 pounds. The bikes are quite light. You can see people on the courses lifting them up by one hand all the time for repairs. So they're usually fully carbon, but that's conservative. and then an impact time of 1 second being extrapolated from our crash video that we had. And then that just gives us an impact force of 345 pounds. That was our starting point of where to look at with like strengths of materials, holding these barriers together. What are we looking at when a biker comes crashing through, or multiple bikers?
And then using that 45 pounds, we were able to input that and a model of a fence that we created into ANSYS, which is a finite elements analysis software. As you can see, I set up the force to be coming perpendicular because we assumed rightly that it would be the highest reaction force. You can see that the Y reactions, which would be vertical, are nearly zero, or negligible in this case, because the biker is obviously not coming down at the fence or up towards the fence. And then you can also see that the X and the Z reactions are inverted based on the angle at which the biker approaches or crashes into the fence, which makes a whole lot of sense because as the biker is coming in parallel, it's going to cause more normal stress on what our solution would be. And when the biker is coming in perpendicular to the fence, it's going to cause more of a shearing on our solution. And so now we know, and we can calculate whether our solutions will be able to withstand a crash in the future or not.
Yeah, so in addition to all the math side of things, we also researched existing solutions and maybe technologies and patents that exist as prior research. So we found a lot of patents and existing technologies as they pertain to holding fences together for like crowd control, so concerts, busy events like that. But these events are just made for exactly that. They're not intended to have people running into them at high speeds. So you often have exposed sheet metal and things like that. So the existing technologies work great for holding fences together, but aren't anywhere near what we need for safety requirements. And then there is existing whole technology systems that are out there, such as like this bow plan barrier system that's used more commonly in like Europe racing series, I know. But it's a very expensive system that you need to buy into. And something like this would be out of scope for this. We're trying to use the fences that currently already exist and not trying to buy into a whole new system. So going over the specifications that we developed for kind of our gray box solution. So without even doing any design work, we developed specifications based on criteria and discussion of the problem. So we're trying to keep our solution, whatever it is, under 1 pound per piece, because whoever is setting up these fences needs to carry a lot of them with them and set them up. The size just needs to fit around an envelope of about 1 by 1 inch for the fence. The budget, we're aiming less than $1,000 for our total prototyping with a manufacturing cost of about $3 per unit. The service life, we're aiming for a minimum of 10 Tour of America Dairyland seasons. Maintenance, we're specifying that this part has to be checked after an impact event to see if it can be reused or needs to be replaced in case of damage. Finish, it of course has to withstand corrosion and decay, especially from outside elements. And with outside elements, it has to be able to withstand rain, snow, and sun, anywhere from 0 to 50 degrees Celsius. You never know, it's Wisconsin after all. And then with testing, we're looking to do static stress tests as well as dynamic testing with a pendulum to simulate biker impact at multiple angles to test our parts. And then the safety, this part of course can have no pinch points to riders or the people setting it up and has to protect riders during a crash event. So going a bit more in depth, the connector performance must be upheld under a variety of conditions. So this part we want to have work as intended before, during, and after crashes. We want it to be able to withstand an event, but also work in all scenarios. It has to work. We're saying if a biker crashes at 30 miles an hour, anywhere from 180-degree range. So whether the biker is just shearing into the fences and kind of tipping into them or getting bumped into them, or if for some reason, let's say their brakes go out and they unfortunately go head on into a barrier, we want it to work either way. And then also work in all weather conditions. And then the big one that we're also working with our design is that the installation and disassembly must be quick and easy. We're aiming for only one person is needed to do this with no power tools or ideally any additional tools. And then you can remove these at any one time so that if like medical personnel or assistants needs to get onto the race course, you can just quickly disattach, get on, get out, put it back, no issues. So with these specifications, a fast diagram was created. just covering alignment of fences, the quick and easy installation, the quick and easy disassembly, being able to withstand crashes, the protecting all the involved parties, and then withstanding environmental effects. And then we also did a feasibility study. So we took all of our specifications, ranked them on a feasibility scale of 0 to 10, and then provided justifications and explanations for all of those things. And then any of these in-depth things that we're glossing over can be found after in the appendix of our report if you want in-depth information.
And with those subfunctions, we moved on to concept generation. When we first created the subfunctions, we knew that we were going to have to go into generation, and we went with some of these ideas. These are just a few sketches that we created at first that just fit one subfunction, and then later on we put them together to try to complete everything that we wanted to complete. And when we were putting them together, we realized that we wanted to pursue 3 different types of materials: metal, polymers, and fabrics, because each of them provide their own benefits and have their own downfalls. So we believe that testing testing 3 different solutions will be helpful to Toad in keeping both their budget, their crash requirements, and their safety needs.
Yeah, looking at the concept generation for the alloy solution, initially we were looking at a fixed end for the barrier and some sort of material in between to compress so that you can change the angle, or something more akin to a cuffing system that'll go around both ends and keep them tight. The alloy solution's strengths will mostly be the alignment, withstanding crashes, and its weather resistance.
Yeah, so starting with we're starting with polymer solutions, knowing that polymers are a very free-form manufacturing processes, commonly additive manufacturing, 3D printing, or injection molding, really pretty unrestrained geometry requirements. So focusing in on what material works best per our specifications. And then also the geometry, what geometry is going to be best for the safety of the riders. Something nice with a lot of surface area to disperse impact and make it nice and squishy if a rider runs into it.
And then we decided to pursue a fabric solution. Some of the benefits for a fabric solution would be it's easy to manufacture and work with. Ideally, it would be able to align the fences very well, and it will be softer than, say, a metal solution or a harder plastic solution. So it would provide a little bit of protection in that way.
Next, for the proposed solutions for all these ideas, after a little bit of iteration, we all came up with physical models for our designs. So I came up with a variable angle clip. So it will, we have a physical product here with us today, but it will clip onto one of the ends of the fence and then twist onto the other side, latching with the square tube. The geometry came from the actual foot of the fence, so hopefully it lines up very well.
Yeah, getting into the plastic polymer solution. This is once again being made of a thermoplastic polyurethane, also known as TPU, which is a pretty squishy, deformable material. So the part was designed such that there's a lip, so that with about only like 5 to 10 pounds of installation force, you just take this part and slide it over your fence, and the lips deform out of the way and snap back to kind of clip on to the thing to hold it in place. And then there's a slit at the top and a curve to help so that you can still set this up at an angle, so that you can have it both on the straightaways as well as the curved sections of track. And then it has a wide, these large bulbous curved surfaces to both support the fence and the structure, and then to provide a nice impact zone that's squishy for riders if they unfortunately meet it.
For our fabric solution, we came up with a bunny shaped product where the bottom section, this long part, will wrap horizontally around the vertical part of the fence, and then these 2 ears up here will wrap around wrap vertically around the horizontal part on top of the fence like that. Those 2 wraps will hopefully stiffen the fence and keep it aligned before, during, and after a crash. And then you may wonder why there's a gap in between these 2. That's because the fence needs to be at an angle. or at, any angle. So with the gap, it gives it the free range of motion without having to stretch out the fabric and therefore diminish a little bit its structural integrity.
Yeah, after that, we looked into a theoretical budget for all we were doing. Obviously, most of the labor is theoretical for a manufacturing look at the project later on. But as of right now, we took into account what we expected the material cost to be for fabrication and design. Fine. Next up, we have the next steps for all of the solutions. At least for the alloy solution, obviously it will be 3D printed to test the fit and functionality of the actual piece. Once we find that it's properly dimensioned and does fit and work as intended, we'll move on to prototyping it with 2 round tubes. We'll be cutting and machining these parts out to fit the dimensions and then welding them together to make the final part.
Yeah, as far as the polymer solution goes, similarly, we've been using iterative testing with 3D printing to refine the design. And then once the design is where we think it should be, of course, after testing, we can go to the next. We'll investigate what the final product manufacturing method will look like. So what is the best at scale solution for this? Because it's TPU, we can probably look into injection molding, additive manufacturing, or subtractive manufacturing, or possibly another solution. Just really researching what's the best, feasible solution to this.
Finally, we have our fabric solution. So the idea for an initial prototype, we can't really 3D print it like the other ones. So we're going to go to a thrift store of some kind and pick out a nice set of jeans and cut them up and use denim as our preliminary check to make sure our dimensions are on point and our the wrapping method is feasible and will in fact keep it aligned. Because if it's not aligned, there's no real point in moving on to the next stage, which will be to make it out of Kevlar. Kevlar is widely known for having a strong tensile strength. So we know that it will be able to withstand a crash. And then it will also hopefully be able to provide the alignment and the ease of manufacturability that the other two can provide.
Yeah, with all of these next steps, we were looking at a schedule for what we'll be doing throughout the next semester. Obviously, we planned out for each different solution, each semester deliverables, what we'll be doing. As of right now, we're going into material ordering and the prototyping phase of it, along with a little bit of design tweaking. Finally, we'll be going into testing for the actual parts. For the plastic and alloy solution, we'll be doing some FEA analysis, finite element analysis, on both the parts with all the previous preliminary calculations. Obviously, we can't do that for the fabric solution as the software will not allow, and also we only work with the fabric's specified properties. After which, we will be taking them to a pendulum swinging test. We will load up a pendulum with some sandbags and go down in the science building. Was the construction lab? Right. Yeah. We'll be setting up a pendulum there and swinging it into the fence. Here we have a code. We have a code that will analyze. Well, that will, based on different parameters, tell us what the length that the rope should be, given certain angles or weights, and what we expect the impact force to be.
Yeah, so, that test using to simulate crashes, of course, and testing all of our parts. So in summary, we researched our initial problem that we were given. We developed specifications for based on that research. We developed solution ideas that we generated. 3 concepts were then selected for further development in the next semester. And then moving forward, testing and validation will be conducted for all 3 of those solutions. And then from that testing and validation, we will give a singular solution that will be proposed for the tour of American Dairyland in May.
Okay, thank you guys. Play up there. Yeah, great. Okay, questions, committee members and code individuals first.
Yeah, so with the fabric solution, how will that be connected? I don't know, do like Velcro or something like that, or what would that?
That's a question. When we're going through the testing phase, we're gonna try 3 different situations for connection. We're gonna try hooks kind of like you would find on a clip-on tie or something. Then we're gonna also try Velcro, and while that will wear out faster,
Yeah.
we are gonna see if it can withstand a couple impacts. And there was a third method that I can't remember. We're gonna try that.
So, I mean, how are you gonna disassemble that? I mean.
Do you mean rivets or do you mean snaps?
Oh, yes.
The snaps.
Yeah.
Snap there. Okay, snap them.
It's permanent. Rivets, though.
It has to be connected always.
When you, in that May, proposal with solution, would you also have ideally, sources for the manufacture of this?
Yes, ideally, we're targeting having a fully flushed solution, with, yeah, all those parts figured out. Manufacturing what it takes, as well, or possibly if we're discussing if it's something like an injection molded part, developing the actual like mold or whatever to reduce cost on that end. So we can do that, so, we're, providing a fully fledged solution in May.
And generally, I'm just thinking about being able to do real life testing on, in our event in June. Would there be maybe sufficient time where you could produce small quantities of, say, the two best ideas?
I certainly believe so, that you guys well within the time
We
frame.
can definitely get that.
Both.
I mean, right now we use zip ties.
You gotta cut them every time.
Oh, yeah,
Yeah. A lot of waste.
yeah. And then, you know, some of the newer staff people cut them and then leave them on the ground.
That's like
And someone else has to come along, pick them all up. So the idea is, of course, cut them and put them in a bag or a pouch, so Andrew's son and I don't have to pick them up at town. So that's, yeah, all these are really, I'd like, little questions about the fabric one, but I think the other two have got some real merit to them for sure. Maybe a third one too. I'm not gonna roll that out by any stretch of the imagination. But really good steps in the right direction.
I got a quick one for you. You're gonna move into the testing phase here pretty soon with like your 3 different ideas. Yes. But it's a bit unclear to me now, like how you're going to decide which one is the winner. Because you have a couple of different like tests that you outlined for the different types. Like, what are you looking at for FEA versus your sandbag thing versus, you know, what actual numbers are you gonna use to sort of understand which one is quote unquote best?
Yeah, I would say, going forward, with all the testing, in addition to just like recording the data and look at it and seeing, you know,
What data?
that analog feed. Oh, sorry. So we'll be taking our, it'll be initially very, what do you call it?
Aspect.
No,
Like qualitative?
qualitative.
Okay.
So we'll have a starting, we'll have the starting force and angle, with this pendulum. So we're simulating multiple impact angles, whether just shearing or directly on, and then at different positions in the fence. So whether like hitting the connector or hitting as far away from the connector as possible.
Right.
And then, so having that and then seeing how each one initially withstands. And then ideally, we'd like to do like, just some, static testing, but not sure how, like with like an Instron or something, getting
Yeah,
an
sure.
actual measurement, but not sure how, valuable that feedback would be,
Right.
compared to like a dynamic qualitative.
I think you
AP
guys-
pass fail.
You have a very difficult problem here because you could like think about welding these things together, but then it's like the cyclist is gonna run into a brick wall, right? So if you think about like the edges of a NASCAR racetrack, they have like these energy absorption, like almost like springs. Or think about like the impact attenuator on your Formula vehicle, right? It's like this honeycomb that deforms and you're looking for energy absorption in a way, right? And so you don't necessarily want like the stiffest thing, but you don't want like the most compliant thing that just gets knocked over, right? So that's what I'm saying, like, how do you really determine which is the best? With some sort of like metric behind your testing.
Yes, we actually, earlier on with our sub functions, before we started, designing initial like things, we had a few different like mock-ups that we weighted different parameters on and graded them on based on like how like good they would be withstanding a crash. Obviously, like an alloy solution would be much better for that. Or like for comfort and like not harming them, obviously like the plastic solution would be a lot better. I think once we get into the testing phase, be able to wait, hey, is this gonna be like, sure, it like holds up, but is it gonna actually hurt me? Or is it like, is it reducing the is it reducing or increasing the safety of the riders coming in contact with it?
Yeah, that's right. So there's a whole field of study about energy absorption and impact, right? And it's area under the curve, low displacement curve, basically. So when you're thinking about your testing, maybe you're thinking about a low displacement area under the curve, kind of how much energy can we absorb without it just being like a brick wall kind of thing, right? I don't know exactly how you do that with your testing, but I think you should be more deliberate about an actual quantitative metric rather than just, oh, we'll see if it falls over, you know?
We'll have to iron it out before we actually get into testing.
I think,
Other questions?
Kevin, so, it's possible that one of the designs could work really well in a straight section.
Uh-huh.
With some flexibility, and some might be better adapted in corners.
Yeah, maybe.
And I guess we do use them in corners, so, there's not necessarily one shoe fits all,
Sure.
this project.
Right. Idea
But,
is hopefully
you know-
we can get one shoe, but maybe we need two.
Yeah. Well, two shoes should be kind of go together for a lot of people.
Okay, we can open it up to, are there any student questions?
I got one.
Go ahead.
That video of the crash, all the fences fall basically at once. Is there any way that you can reduce that happening, or are you gonna try to do?
Yeah, so that we've thought about that in a few of the design process. That wasn't listed as highly important or as important as a criteria. Especially because right now they're already zip tied together and that event is already happening. But one thing so kind of like with the plastic solution, for example, it has that clip. And the idea is that one, it functions as like the human can take it and clip it onto the thing. But then its open face is away from the drivers or riders. So if a rider were to hit a fence, ideally there's just the right amount of deformability in the lip that the rider can kind of like break through it. Like like after a certain amount of force happens, it gives way and the rider's able to pass through the fence. And then only a small section falls as opposed to, 10, 20, 30 fence pieces.
And not only that, but it's also, like I talked about at the beginning with this current solution at the feet, where there's two like tubes sticking out the bottom. The way the fences work is the feet like stick in. So when the rider hits it and it falls over, if that foot doesn't either snap off or like slip out somehow, all the other fences will come down with it just because that's how
By nature of the
cast
design.
So I mean, initially, we did look at modifying feet or some sort of like 5-foot break point. That like every like 5 lengths of fence, there would be,
Don't have a,
yeah, there would be a special clip on top, and you'd like modify the foot to like break away if it were hit, because that's one side's rigid. But we haven't quite pursued that, but if we find that you guys would like that, we can totally go into that.
Yeah. I want to give one last comment about your Kevlar idea. Kevlar in the sun for long periods of time is not good.
Yeah.
So if it's not like reinforced, like it's not an epoxy, right? So Kevlar is often used as a reinforcement.
Yeah.
If it's not like protected by some matrix phase, then the fabric itself in the sun is going to deteriorate.
Yeah, and that was one of the downsides of our fabric solution, was that it will deteriorate faster than the other two in the sun. But all of our solutions have their give and takes, and we decided that using Kevlar would be the best option, given.
10 seasons? Oof, I don't know.
Yeah, it won't matter.
Well, I was gonna say, their given spec was 5 seasons. We tried to beat it by upping it to 10, but
Oh,
you see if we can meet that.
Double it or nothing.
Yeah.
Okay, I think we'll have to move on to the next talk. Let's take a break.
This is for you.
Thank you very much.
Thank you.
Good job. Holiday parade. No, no, no.
Great, thank you.
Thanks for coming. You're good. Thanks for coming. Yeah, good to see you too. I know, only for a short minute here, but yeah, Andrew, good to see you.
We got other things to talk about.
Yeah, sure. And I did see your, yeah, we'll talk.
Yeah.
Yeah.
For sure. Thank you. Good luck. Thank you.
So. We're going to have Lizzie arrive. You wanna?
Not today.
That's it.
We actually did separate presentation.
Okay.
2 weeks ago.
Okay, cool.
Yeah.
You want to hit the ledge just a little more clear. All right, so next talk is the solar pool cover design. This is with a couple of engineers from GE, so. Looks like we have some more audience members who can, no, okay. Go ahead, guys, about 20 minutes of the talk and then Q&A.
Our project was a solar pool cover redesign by GE Healthcare.
So what is a solar pool cover? A solar pool cover is a barrier between the water and the atmosphere that prevents energy loss by reducing evaporation. Its main purpose is to absorb solar energy and then transfer that energy into the water to heat the pool. A lot of homeowners buy this type of cover because it does reduce evaporation. It's an insulator, so it reduces heat losses and it reduces the overall cost of heating the pool. Currently, this cover is made out of polyethylene or polypropylene, and it has a bubble design. However, this bubble design can fail in 2 ways. The first way it can fail is when the flat surface of the cover begins to peel away from the bubble that's surrounding the material. The material that's surrounding the bubble, which is seen in this picture right here. And the second way is when the bubble starts to separate from the cover in part or in whole. This is caused by contact with pool chemicals and exposure to UV radiation and the sun. And these failures mean that the covers last only 1 or 2 seasons, and the fragments that start to come off the cover gets into the pool drains and the skimmer baskets, which creates more work for the homeowner overall. These failures also increase the amount of energy loss that the pool experiences, with 70% of these energy losses being from evaporation and 30% of these losses being from convection and conduction. Due to these issues, the team decided that the overall goal of this project was to reduce thermal energy losses in a way that addresses quality issues. We then went into our research portion. We began with broad research, which really included things that didn't have a lot to do with covers, so pool floaties, pool lane lines, and pool plaster cover, which doing this type of research allowed us a little more avenues to go down when creating possible solutions. And maybe like thinking we didn't even need a cover to address these issues. We then went into patent research, which helped us get a better understanding of what ideas already exist for heating units for pools and other potential cover ideas. Along with patents, we also researched some scholarly journals, which gave us some experimental data about what geometry is best for heat transfer, what color is best for heat transfer, and maybe if adding salt into the pool or into the cover somehow would help retain that heat. We then looked into existing products, which just helped us get a better understanding of what's currently on the market and what we're currently trying to make better. From this research, we were able to create a list of 50 possible solutions. And from this list of possible solutions, we were able to narrow it down to 3 main designs.
So basically the process of narrowing it down from 50 to this 3 right here, we started off by obviously making up those 50 ideas and then using our constraints on criteria that we created, we whittled it down even more. But then we got to a point where we couldn't do it just based off constraints and criteria that we created. So then we created a heat transfer model that we will present on later. And we did a little bit of research on materials. And after that said research, we were able to narrow it down to 3 designs. This design actually came later after we came up with our 50, but it is one of our top designs as of right now. Basically, the idea is to have a similar approach to what is on the market right now, but basically getting rid of the bubbles so there will be no bubble failure. We will try and have right now it is a pyramid design. that will be trapping air underneath the pool cover. So you still have that air that is almost a layer of insulation. And then this design is created only using one sheet rather than two laminated together. So there's less modes of failure. And then obviously it's easier to manufacture. The second design that we came up with was similar to what is on the market now, but basically adding another layer of protection from UV to stop UV from degrading the bubbles as seen in the picture before. And then obviously with that increased air in between the two materials, we increased insulation. So then keeping the warmth inside the pool at night or during colder temperatures. This design we have, as of right now, we have two different types of materials. Hopefully one is gonna withstand to the chemicals of the water more, and then the other is gonna withstand to the UV radiation a little bit more. And then the third design we had, we incorporated a thin layer of aluminum in between there to increase the insulation properties so that the loss of heat at night or colder temperatures is minimized. Because we saw that for when we were looking into research, the colors of the pool covers didn't have too much of an effect, but the one that had the most effect in heating wise was a transparent cover. But with the aesthetics and obviously pool owners, they won't like a clear pool cover just because it gets dirty really easily and it's really easy to see crud and stuff like that. So that's why a lot of them are blue. So during the day, usually you don't have a pool cover because you're using it. So trying to keep as much of the water in from evaporation and heat in as possible at night and during colder temperatures. It's kind of what we're trying to achieve here.
So in order to arrive at these decisions, we needed a thermal model to kind of drive those models and material decisions. So as shown here, we have all of our heat transports, conduction through the ground, radiation into the pool, convection out, and our biggest driver is this evaporative loss. So this is modeled at daytime and nighttime. And as you'll see soon, the difference in day and night is a large factor. So in order to create this model, we put in the various boundary conditions throughout a day. So this is modeled for a typical Milwaukee summer day. July 17th is what this is modeled after. Starting at 5 a.m. and progressing through 24 hours with the temperature and relative humidity shown to your left there. And the geometry of the pool is as follows with the figure. So our resulting thermal model with our heat transports, we modeled this under a variety of different materials. A high density polyethylene, medium density polyethylene, low density polyethylene, PVC, and polypropylene. And this really starts to deviate at 8 p.m. when we put our pool cover on. And this, from the material characteristics, really depends on how much evaporation those covers let through and the thermal storage properties that it's allowed to release into the water. So with these heat transports, we had a temperature of the pool versus time curve. As we progress throughout the day, we see minimal losses, but then at 8 p.m., once that sun goes down and you're no longer having that help from that radiation heat transport with no cover, that dashed line really starts to drop down. So the addition of this really drives home the importance of having that solar pool cover to help reduce losses. So we saw that the best performing covers that were able to maintain the pool temperature the best were the high density polyethylene and medium density polyethylene covers with the corresponding evaporative losses shown in table 1.
Drive the thermal model, material selection needed to be considered. On the screen is the materials that are typically used in solar pool covers currently. With high density polyethylene, medium density polyethylene, low density polyethylene, polypropylene, and PVC. The graphs below just demonstrate the properties compared to one another on a visual representation. Other materials were considered, such as PCMs or phase change materials, and liquid crystals. Ultimately, those materials, while having unique properties that will aid in the thermal process, we didn't see it being helpful in solving this situation with quality and rupture of the bubble design. So based on the thermal model, high density polyethylene ended up being the best and cheapest one of the materials that weighed in multiple factors. Heat capacity ended up being one of the driving factors as well as density. To test, we wanted to test whether the bubble was actually critical for maintaining buoyancy on the pool itself. This right here is a material we found in the lab, which is similar to the ceiling covers that are used for the classrooms. They have the design similar to that over there, where they have an imprinted side and one side that is flat. We tested that by putting in a tank of pool water to see whether air bubbles would help keep it buoyant. We found that that helps keep it buoyant and doesn't have any problems with staying above the water. And this kind of aided in our design 1, where we wanted to eliminate the pool design and have kind of a fin-like design. This is a single sheet similar to our first design, which is why we considered it to be an optimal solution.
Moving forward in next semester, we have plans to do validation testing with a high density polyethylene. One test being using the psychrometric chamber to simulate the dry bulb temperature and relative humidity, and then purchasing a UV light similar to the lights they use in tanning beds to radiate the energy, and then test the pool temperature over time and look at the mass loss between our high density polyethylene cover and the bubble cover to make a comparison and see if that bubble is crucial to the thermal properties. We're also going to do a secondary test, which is a manufacturing study looking at different thicknesses of polyethylene covers and
Okay. Thank you. Okay, got plenty of time for questions. So committee members first. Any questions for, I guess you guys are there, but you get to hunt on them all the time. Okay, so I want to be clear. What do they typically make pool covers out of right now? Is it PVC?
Polyethylene, PVC, polypropylene, all of those ones that were in the materials considerations.
Okay, and you say that part of the issue is that the chemicals from the pools will attack those polymers, yes?
As well as UV radiation from the sun.
Okay, so it's both of those things? So it looks like you have a choice in your design of like material that you're going to use, yes?
Correct.
But it sounds like the choices that you have or that you're going to make are all of the choices that exist previously. So what benefit would going with something that already exists have if you think the UV degradation and chemical pools, et cetera, is going to still basically eat away at your cover,
I
right?
think a large factor is with the thicknesses. So if we go with a single sheet, we're not having that a 2 lamination to create the bubble, and we're able to kind of go with a thicker option that is a little more resistant to that chemical degradation, UV.
Okay, so is it chemical? So, I mean, there's two things happening here, right? There's the UV and then there's the chemical. Which one is like more impactful when it comes to failing to previous pool covers? Do you know?
I would say UV, but
UV is more-
another failure, so if you go back to the beginning of the slide where the pool cover is shown, a lot of the failure, these covers are not made to fit all covers, so a lot of people ended up cutting to fit their pool
Sure.
sizes. So a lot of the failure occurs at these seam points where a lot of the UV degradation starts and continues as it grows. So a lot of it is also just the fitting onto the pool. So one of our ideas is to kind of make it a modular design, so if failure does occur, we can replace smaller units within the cover.
So what's your plan then for UV protection? I mean, are you still gonna think about like putting that aluminum layer on the top? Is that still possible? Is that that was the reason for the aluminum layer, was for the UV protection, is that right?
Correct.
Yes, and then also to help with the insulation of the pool during like colder temperatures and, you know, nighttime when it's not that warm out.
So have you settled on a final like design choice, or you have like more things to do? It's a bit unclear.
We haven't really decided, set in stone on design. We still have to run a few more tests just to see like how each material acts with UV radiation and then as well as chemicals. But these are kind of like our top choices as of this moment. Next semester is going to be a lot of testing to see whether the bubbles actually help in the thermal aspect of things or they're just used there for buoyancy. Because if they're really don't do that much with the thermal aspect, that's why we kind of want to go with that first design to minimize manufacturing costs, then as well as
First thing you're talking about just the triangle.
getting rid of the bubbles. Yes.
We foresee when we get rid, if we need the bubbles or if we get rid of the bubbles, that UV will not be as big of an issue without the bubbles and the delamination being a single sheet of polyethylene. It'll be less degradation of the actual cover and less failure to the actual cover.
Because most of the issues are at the lamination points, not really the actual material itself. So, yeah.
Okay, so what tests are you planning to do then? You're just gonna put this in like a UV box for a while and see what happens?
Basically what we want to do first is to put a cover that has those bubbles and then one that is just a single sheet. And just to see how much that affects the heat transfer and thermal properties of it, just to see how the water reacts. And then see if those bubbles are necessary or if they're simply just for buoyancy. And then based off that, kind of narrow down.
Okay, any plans for any like chemical tests? I mean, like, obviously chlorine is a very common thing that gets like put into pools. I mean, would you try to simulate like water of an actual pool by putting some like chlorine in it, putting it on there and like see what happens?
We want to do a test where we have a bucket of pool water in essence, and then put a cover on top, put UV on top of it, see how long it takes to degrade the material.
From like a data perspective, to make those decisions, we're gonna use thermocouples and adapt to actually grab temperature measurements and then measure the mass after our study to see the.
Have you made a prototype? Like, how do you plan to make your triangle prototype, let's say?
So we were floating around ideas about
Floating around?
very good. Ideas to basically get the material and then use something like you know, a meat tenderizer or something like that, just to have something that is like
That's imprint to the
shape or of some sort, because obviously we're not gonna be able to make this exactly how we want it using polyethylene just like on our own. We also talked about using a waffle iron and just melting it in.
Not a bad idea.
So yeah, we had a few ideas on how we we're gonna prototype it. We haven't narrowed down one that we are set on yet, but obviously this is a manufacturing process that's kind of hard to do DIY. So
Yeah, right.
trying to figure that out as well as see how we're gonna do that. And that's one of the tests that we plan on doing next semester, is to see how easy it is to create those different shapes in that material and how like you know, when you heat it up, if you make an imprint of a shape, how is it gonna affect the material and stuff like that?
Seems like a challenge.
Go ahead. Question, follow up on Professor Hart. How, since you've identified degradation as a serious issue, how are you going to evaluate the degradation question with your different designs? You said that you were gonna maybe expose it to chlorine water or expose it to UV. For how long? The degradation is something that happens over time. So how would you evaluate the degradation for your different designs, since you have identified that as a major factor?
Testing for life is a very difficult thing just because we don't have a lot of time. So we haven't really figured out how we're gonna test for life at this point in time. I feel like if we could try and up the, you know, radiation or whatever based off of that UV lamp, see how it would, you know, act under stress, to kind of give us an idea, but I don't know if we can say for how long it will last, just because you would have to have it under those conditions for as long as it takes for them to degrade, and we don't have that luxury of that much time.
So you don't have the luxury of doing the life testing. I guess I understand that. But again, since that is a major factor in your design, by the end of the day, you're going to have to say something about the degradation. Okay, we have this new design, it's a better thermal model, but we have no reason to believe the degradation would be any less than it is. You pointed out one factor which is important, which is the delamination. You said that a lot of the degradation has to do with delamination, but is there additional degradation beyond that? Is that the major issue, is the lamination, or is there degradation of other sorts? It's flaking or whatever, you know, loss of
It
strength.
seems like through validation testing on performance, if we say from a performance perspective, we can get this single layer to work, then the main failure modes are between the delamination between the two materials and the bubble degradation. And with that single layer design, we don't have two layers that could delaminate, and then we don't have a bubble that fails. So if we've kind of eliminated those two failure modes, then from a performance perspective, if we can say this one sheet will work, and we've eliminated the two failure modes, like that's a large factor.
Okay, so what you're saying is it isn't the material degradation that's the major factor. It's the degradation due to the manufacture of or the design of the particular type of cover. But I think that's something you should be clear about, because otherwise you're gonna end up with a design that, well, it's the same material as before. Isn't it gonna degrade the same way? So I think you're gonna have to make clear, here's what our failure modes are, and here's why we consider this to be better.
Yeah, so the way the pool covers are made right now, right, it's almost like a sandwich structure. You got the top face sheet, the bubbles, the bottom face sheet. Yes, and you're saying that over time they'll separate. Yes, that's true. So why do they have a top face sheet and a bottom face sheet if you've shown that you just need one?
We believe that it's for buoyancy.
Yes.
So from like a usability standpoint, I think it's easier from the user's perspective just to be able to throw this cover and it floats. But if we find that through our single sheet design, if we have enough buoyancy with the trapped air, then we're going to eliminate that.
Yeah, when you have the sandwich structure, there will be air trapped in there, no doubt about it. There's no way that water can penetrate that, right? But if you just have one layer, like you guys are proposing, and then like triangles coming down, there is a possibility for water to get entrenched into your pyramids, right? And which case you're gonna sink, which is not ideal, right? So I think you have to be very careful about user error when it comes to like applying this, right? Because you can imagine somebody that's not really like understanding what's going on, just like throwing this thing in, and then all of a sudden the air, water gets in their little pyramids, and all of a sudden this thing is sucked to the bottom of their bowl, right? They're like, what happened?
What is the density of the material?
It's
Which material, the high density polyethylene?
Yeah, compared to water.
Well, yeah, the
Definitely.
polymer itself will be higher density than water, right? Usually about 2 grams.
The density was 959 kilograms per meter cubed.
Oh, so it's.
It's less than-
Yeah.
So it's.
So it should flow.
Either way. So it doesn't even matter.
Yeah, so
Right.
that's kind of the driver when we're like, why are
So
they
it
putting
makes
these
no
bubbles?
sense that they would even have like a.
It seems like it's just an industry standard. It seems like it's just an industry standard that it just kept propagating. So that's why we're investigating whether the bubble is even necessary.
Okay, interesting. All right. Other questions, students? Okay, thank you guys. Oh.
Hello.
Do you mind if? I would take some time.
Yeah, it's definitely. I usually don't fill them out all the way. I just have to give the overall grade on the back.
Sure.
And do with it what you want. You know?
Yeah.
The video still hanging on.
Yep, it's like no one's hopped in yet.
Yeah, that's not. It's mostly about recording. All the crew here today.
Yeah.
We're a little ahead, but I think we have everyone for this here. I think we can go ahead and get started. So this is the last talk in the session with Delta Hawk composite truss structure advised by me. Go.
Okay, so like you said, carbon fiber Delta Hawk aircraft engine truss structure, sponsored by Delta Hawk on Large Composites. I'm Tony.
I'm Hunter.
I'm Cole. I'm Bryce. I'm Max.
So a little background on Delta Hawk. They are based in Racine. They make a special twin charge inverted V4 two-stroke diesel engine. This engine offers improved performance, fuel efficiency, and reliability over traditional aircraft engines. It has many applications on smaller aircraft, and they're the ones that proposed this project. So the problem statement we made from their proposal is Delta Hawk Engine seeks to develop a versatile carbon fiber mounting structure that attaches their DHK 235A4 engine to the frame and firewall of a single engine aircraft. The objective is to provide a lighter mount than the currently used steel one, while complying with FAA CFR Part 23 standards. And since we're using composites in here, Delta Hawk is partnering with Amalgam Composites. They're going to be making all of the tubes for us during this project. They specialize in carbon fiber drive shafts and glass fiber tubing.
So before we came up with any designs, we wanted to look at some of the designs that Delta Hawk currently uses. This is one of them, is the easiest to see. It's the white tubular structure here. In the top left, it's the triangular metallic structure. And in the bottom left, that's actually the plane that our truss will be going into, which is the SR20. And it is that gray tubular metallic structure there. And we wanted to make sure that we didn't interfere with any of their wiring harnesses or tubing. So that was one of the considerations that we took into account.
So again, the objectives and constraints. So one of the main constraints is our design shall fit in the engine, the aircraft's engine cowl. The firewall mounts, the bearing mounts, and the landing platform were all fixed positions. We could not change where those are. And we also wanted to comply to all FAA regulations regarding forces. That just meant that any load cases dictated by the FAA, our truss structure would survive the forces generated by those. And this would all be found in Title 14 CFR Section 23, which are all the rules and regulations needed for normal category aircraft, which is what the series falls under. The objectives were fire protection. When reading through the FAA regulations, they did take into effect thermal considerations, and that is the engine truss structure need to be capable of withstanding the effects of fire, which they defined as a temperature of 2000 degrees Fahrenheit for 15 minutes. And then also we hope to reduce the static weight of the current truss by 20%.
Once we came up with those objectives and constraints, we wanted to come up with some subsystems. So I was in charge of the tubular structure of the truss. Cole
Cole was in charge of the joinery and assembly. Max was in charge of the FAA rules and regulations, as well as the validation through FEA. Bryce was in charge of everything to do with composites. Tony was in charge of the thermal insulation, as well as our project leader. So we wanted to look, or here's a image of their current truss. There's two different views. The orange, green, and purple highlights are the mounting positions that Max previously mentioned that we cannot change as those are fixed. The orange, which is a bearing mount, that mounts the engine directly to the truss. The green is the landing platform, which mounts the landing gear to the truss. And the purple is the firewall mounts, which mounts the truss to the airplane itself. Here's another view. As you can see in the isometric view, the truss is perfectly symmetrical about the midpoint. So we wanted to look at their current design if we made that directly into a carbon fiber reinforced polymer or CFRP. So some pros with that is that it has a good stress distribution, but some cons with that is there's many members and joints, and of those joints, they're very complex. So here's all these red circles are all the joints that we'd have to take into account. And this is only one side of the truss. It's the exact same on the other side. So we wanted to try and figure out how we could get rid of as many members and joints as possible. So we came up with some designs. So we came up with a lot of designs, but we kind of narrowed it down to two different ones. This is the first one. With this design, we wanted to try and move that top bar forward away from the turbocharger, and that would help us with some of the thermal considerations that Tony will talk about later. As you can see in the left picture, the blue circles and arrows indicate how we kind of compiled the joints together to decrease the number of joints, but we made them a little bit more complex. And the red highlights are bars that we just got rid of to try and decrease that number of members as much as possible. And then we came up with another design, and with this design, we moved the top bar forward and up. It wasn't so far forward, but we moved it up a little bit. We got rid of 3 bars, but we actually added 2 back because we wanted to ensure that the truss had enough structural rigidity and torsion. And with this design, we also tried to compile the joints as much as possible. So after that, we wanted to create a decision matrix. And a decision matrix, pretty much you have your designs listed, and then there's categories, and they're judged based on those categories. And each category is given a weight. For example, in the second column, the number of joints was given a weight of 3, which is really significant because we wanted to decrease the number of joints as much as possible. The second design won in this decision matrix, and we decided to move forward with that to some more down selection and validation. So here's our final proposed truss design. As you can see, there's a lot less members and a lot less joints. In the blue circle, that is one of the joints that we had to consider changing the geometry of because of the joinery that Cole will talk about later. And we wanted to increase all of the tube thicknesses to ensure that the truss will be able to hold all the loads because of the number of members that we removed. And we validated this through FEA.
So the goal of the FEA was to compare our current design, or Delta's current design, to our proposed redesign. We look at the stresses in each member to prove that our redesign didn't overstress any one member. And this would also be used to find the internal forces and moments acting on each member, which would be needed when converting the current steel members to composites. So for validation, Delta Hawk provided us with reaction forces at the firewall found in FEA. So we used a simple load case of 6.6 G's acting on the center of gravity of the propeller and the engine. This would be, if you nose the plane up, it would be the force trying to pull the engine and the propeller back down. And then we also use the propeller thrust load. We modeled Delta Hawk's current truss model in ANSYS using shell elements. You can see there the comparison of the reaction forces at the firewall mounts. Looking at the major reacting forces, we had a percent difference of about 18% maximum. So we felt that would be good enough to move on to the stress analysis. So at this point, Delta Hawk did not provide stress analysis on the truss, so this would be all new data we were finding. So shell element model, like I said, was previously made of Delta Hawk's current truss and our proposed design. At this point, analysis in ANSYS was done using entirely steel still. And then we found no significant stress difference between our model and Delta Hawk's current model. As you can see there, our model does as good, if not better job at distributing the stresses. So we said that would be good enough and our design would work. So we moved on and made it in beam elements. The beam elements were used as they are good at finding internal loads and moments acting on each member. And those internal loads and moments would be needed for sizing the composite tubes.
So since some composite materials are a primary material used in this, I got some background research on them. Composite materials are typically used in the aerospace industry for their excellent strength to weight ratio. Truss structures, typically they use tubes for a majority of their members, and the best manufacturing method for composite tubes is a filament winding process. Amalgamous filament winding process is shown in the picture on the right. In the top left, fibers are being pulled off of spools and are being fed through a resin bath, essentially wetting the fibers with resin. Those wet fibers are then wrapped around a mandrel, and then the resin is then cured and the tube is extracted from the mandrel. With a filament winding process, the user can specify a wind angle they want. These two images in the bottom left show that the wind angle is with respect to the center line of the mandrel. The black lines are indicative of the fiber direction. One limitation of a filament winding process is that you must lay down a positive theta wind angle and then a negative theta wind angle before you change that wind angle. So in other words, if you wanted a 30-degree wind angle, you must have a positive 30, then a negative 30, and then you can change that wind angle. Another limitation of filament winding is you must typically stay within a range of plus or minus 30 degrees to plus or minus 60 degrees. I did need to do some composite material FEA in this project, and for that I used ANSYS's composite pre-post toolbox, otherwise known as ACP, for all the non-isotropic material FEA. I did a quick validation of this to prove that my model that I have now and any future models that I create are good. For this, I made a simple thin 4-layer stacking sequence laminate and applied a fixed support on one end and then a simple axial load and torsional moment on the other. I then used ACP's post feature, which lets you analyze the strains in each of the layer and the fiber direction. And then I compared those strains I found to that I found using classical lamination theory in a MATLAB script I created. Classical lamination theory assumes that the laminate is a thin plate and makes us take into account primarily just in-plane loads, which simplifies the analysis a little bit. Comparing the ACP and the CLT script, layer 2 produced the highest difference of about 15%. This is not a negligible difference, however, it is not enough to warrant concern. Some initial design concepts I had to take into account for the composite tubes. On the current Delta Hawk truss, the members either have an internal diameter of 5/8 inch or 1 inch. As we transition to composite tubes, those inner diameters will remain the same for the respective members. So the 5/8 inch will remain 5/8 inch and the 1 inch will remain 1 inch. The stacking sequences that I do test and will downselect to must incorporate those limitations of filament winding. So again, that's that plus or minus alternating stacking sequence, as well as incorporating that plus or minus 30 to plus or minus 60 degree wind angles. And then all the calculations that I did by hand in this project are using the assumptions of classical lamination theory. And since the composite needs to be a thin laminate for that assumption, we have to assume that we are unrolling our tube into a flat plate. To show that this is an okay assumption to make, I did a quick ACP validation. I made a composite tube with the same stacking sequence, same boundary conditions, and the same dimensions as the plate that I mentioned earlier. By that I mean the circumference of the circle is the same width as the plate. The analysis produced an 85% difference in the strain and the fiber directions, which is quite a high percent difference. It shows that this is not a great assumption to make. So to counteract that, we are going to go with a minimum factor of safety of at least 1.5 for a prescribed stacking sequence. These are the internal load cases for each member found from Max's beam element FEA results. These are then the loads I will then use along with failure theory and classical lamination theory to find a stacking sequence that will work for us. I'd like to point out one thing here. Member 1, that long structural member, is the most important member, sharing a majority of the load and has a lot of combined loading. As far as testing stacking sequences, I tested 5 of them, and they do all incorporate those limitations I talked about for filament winding. And then as far as failure criterion go for composites, there's a couple of them. I did choose the most conservative one when calculating the safety factor. After calculating all of them, stacking sequence 3 produced the highest safety factor for a majority of the members. The only member that did not pass on any of the stacking sequences was member 1, that structural important bar. And in order to get that to a minimum factor safety of 1.5, I did have to double the stacking sequence, which is in essence doubling the wall thickness of the tube. I think this massive discrepancy is due to the classical lamination theory assumptions that we're making for tubes.
So now that we have the composite tubes picked out, as well as the geometry for the truss itself, we have to look at how we're going to actually join these members together to make this whole truss. With the current Delta Hawk truss, it is made out of steel, so it's pretty easy to be able to cut, cope any of those tubes and just weld them together. The problem comes up here is that composite tubes, you cannot simply weld them together. So we have to look at how we could actually combine them using either composite or metal joints. Looking at a sample composite joint here, you would have a bladder molded process. This is a die, as you can see here. So this would kind of form your outer shape or geometry of the joint. Then you would lay in your fabric of the composite. You would lay in a bladder or basically a balloon. And then once this die is closed, you would inflate that, which forms the inner geometry of your part. The nice thing about this is that you would have the low density, which would be very nice to match that of the truss structure, as well as the strength to weight ratio, as Bryce had mentioned, is very nice for composites. Looking at the coefficient of thermal expansion, this is also very nice due to the fact that you would actually match that of the composite tube. So when there's heat added, you don't have any residual stresses in there. The only downside of this method is the feasibility of it. Looking at this, every single joint we would make would have to have its own die as well as its own bladder made. So it's kind of out of the scope of this project in terms of cost and time considerations. So that is why with our decision matrix, we ended up going with metal joints. Looking at what metals we wanted to go with, we picked 2 aerospace grade aluminums to compare, as well as titanium to look at the differences with the current steel that Delta Hawk uses. Obviously, we wanted to consider the strength, density, and cost as these are main considerations. And again, that coefficient of thermal expansion, we want to make sure that it doesn't expand too much with comparison to the composite, just to make sure there are no residual stresses. Lastly, we want to make sure that it's actually weldable and machinable, as some of these geometries will be pretty complex. We don't want any work hardening limiting us in those factors. With our decision matrix, we ended up picking a 6061 T6 aluminum. This is purchased as a raw material, which we can get pretty much any supplier, and then machine it down to whatever geometry we need for our later considerations. Looking at how we'll connect this aluminum to the composites itself, we did a lot of research on that, and these are the 3 best methods we had found. The first one on the upper left there is an adhesion method. On the left there, you have a composite tube with a metallic insert. In this case, it would be aluminum. So you would insert that in, and then you would have your adhesive in there to spread out that shear force and just actually hold the load coming through that joint. This is very manufacturable. It's hard to repeat. So that is the one thing we took into consideration. Something compared to the pin method is very simple to manufacture. You would simply drill through the composite tube itself, as well as the aluminum, and then you would put a bolt or a pin there, and that is what carries your load. The problem with this method is when you drill through that composite tube, you are cutting the fibers. These fibers are what carry all that load, so cutting them carries very high stress concentrations, so that's a big limiting factor with this pin method. Lastly, the wound insert, it is kind of a combination of the two. You have the benefits of the adhesion as well as the pin. So you can kind of see here that insert would be there. You would actually put this on the mandrel when you manufacture it, and you would wind the filament around it so that you kind of have that locking as well as that adhesion there. The only downside here is that it's very hard to manufacture. Like I said, it would be put on the mandrel, so each tube would have to be made specifically just for this, and then it's hard to combine at a joint afterwards. Looking at our decision matrix, we ended up going with the adhesion method, as it kind of combines that strength distribution as well as the manufacturability. And this leads us to the fact that we need to pick an adhesive that we'll use to combine the two. For an adhesive, we went with looking into 2-part epoxy-based adhesives. We wanted an epoxy-based adhesive, as the fact that the tube itself will be epoxy-based in the matrix. This will provide us with the strongest bond, and we wanted to make sure that the bond between the aluminum and the composite tube is as high as possible. Another thing considered was the working time. When we're actually assembling this truss, we want a little bit of time that if we do line something up, insert it, we want some play in there. That way it's not aligning properly. We can move it. We have that, whatever, 20 to 165 minute range. We want to take that into consideration as well. Lastly, here, we want to look at the cost, which, obviously this is on a budget, and we wanted to look at temperature due to the fact that it is in that engine bay. So as the temperature rises, we don't want any loss in that shear strength. From our decision matrix and looking at all these considerations, based on the manufacturer specifications, we picked 3M's DP420. While this is all great due to the manufacturer specifications, we want to make sure that in our actual configuration that this does hold up as we expect. So next term, I have already ordered all 6 of these adhesives, and I plan to test it using that insert there, which will fit right into the Instrom for some tensile testing to look at how these actually add up compared to what the manufacturer stated. As far as actually putting these to use in our truss design, we wanted to kind of keep that 1 inch and 5/8 inch ID for those tubes. So we'll have 1 inch and then the 5/8 inch inserts, which we can then use to machine down as a coping and mount to any geometry that we pretty much need. So in the upper right, you can see that this is the upper firewall mount. So that would be bolted to the firewall. You would have a 1 inch tube coming off where that would slide in over this, be bonded there, and then a 5/8 inch there as well to be bonded in. As far as some of the impossible assembly sequences, once you get these complex designs, it's very difficult for us to be able to insert everything as we would like to. This made us have to come up with something such as this clamp right here, where we were able to actually make one side of it, adhere it, and then once that's all done, bolt them together, add adhesive, and then your strength is regained there. Looking at this in the actual whole view, this is a little preview of the truss design. You can see that top firewall mount in the very left there, joining that 5/8 inch ID and the 1 inch ID tube, as well as the clamps. That way we can actually put that piece together in the end to form the whole truss.
All right, so similar to how we had to relook at joinery, we also had to relook at thermal effects. And there are 2 main considerations. The left picture shows the engine bay with the turbo highlighted in red, which will get up to a temperature of around 1400 degrees Fahrenheit, which is far above the maximum temperature that epoxy used in the carbon fiber, which is only up to 350. So any member near that turbo will need to be insulated. Additionally, on the right picture, you can see the engine cowl with the top removed, and at operating temperature, the engine will get up to around 300 degrees. So just like Cole was saying, we're going to need to insulate the adhesives to protect them and keep their strength. So to start, I did a bunch of research on different industries and areas and compiled a list of just different methods. And from there, I was able to down select 3 choices: silica aerogel, calcium aluminum silicate, and aluminum. Now, I ordered these 3 off of McMaster Carr in tape form and did a calorimetry experiment just to see which one had the best insulation. And while silica aerogel was the best at insulating, it was not the one I wanted to choose, simply because being able to physically handle these materials showed me that it was tough to work with, it made a mess, and frayed really easily. Therefore, alumina, which worked a lot better, was the one chosen for this project.
Here's our final proposed truss model. As you can see, there's different highlights. The orange, green, and purple again are the mounting positions that are fixed, and we did not change those. And the blue are the clamp joints that Cole came up with. And the red highlights are aluminum members, which were members that were too short to fully utilize the effects of carbon fiber tubing. So they are aluminum tubing instead. In the isometric view here, you can see that the truss is still fully symmetric about the midplane, and we wanted to do that to increase the ease of manufacturing and assemblability.
So for some of our final design considerations, the current Delta Hawk truss does have a static weight of about 26 pounds. Ours is currently way above that at 40.1, which we did not meet the objective of the 20% weight reduction. However, we have not weight optimized the tubes or the joints. Next semester, that will be our first focus. I will focus on the tubes by using the ACP to do failure analysis instead of using the classical lamination assumptions. As far as the number of members go, we were able to cut down to 21, and then the number of joints down to 30. Thank you guys for coming to the presentation. We now have time for questions.
Just one, it's probably, don't watch out there. That's fine. Okay, time for questions. Committee members first. Go ahead.
Can you go back 1 slide, please? So between the current truss and the proposed truss, so the proposed truss is using the composite material.
Yep.
So in your proposed truss, you've decreased the number of joints. If you're just using the typical steel that the current truss is using, is there any weight reduction there, or are you adding weight by decreasing the number of members?
The main reason there's a huge add in weight is because of those classical lamination theory assumptions. Since there's such a big difference, I did have to kind of over-engineer these composite tubes. So there is way too much carbon fiber on those tubes than there actually will have to be. So that's pretty much there. And then as far as the joints go, those will just have to they're kind of blocks right now, so we'll just have to get them into an optimized shape.
Yeah.
Yeah, so once we figure out that final tube outer diameter, we'll be able to pick the clamp inner diameter, and from there we can machine down rather than a big block, we can actually have it optimized quite a bit.
Yeah.
I think Dr. Hayes is asking here though, like if you just took your proposed truss and thought about making it out of steel, how much lighter is it than the previous? Do you have that number?
We do not have that number.
With the geometry though, it might be heavier because the tube thicknesses are increased as well as some of the inner diameters are increased.
Sure.
So it might be heavier because of that.
Other questions?
Hey, guys, that the diameters, the outer diameters that you chose, we're not married to those. If you need to change them, go right ahead. I mean, you can optimize them with the better diameter. I mean, if a bigger or smaller diameter will be more efficient, go ahead and change it. Okay.
Awesome. Yeah, I have two kind of questions. The first one is on slide like 31, you kind of talk about the epoxy. I mean, the main concern that I guess like the people that I've talked to have about like a carbon fiber engine mount is that it needs to go up to 2000 degrees for between 5 and 15 minutes. And if the maximum service temperature is 350, I don't know if it can maintain that even after it's insulated. Is there any like higher temperature epoxies that you guys know of or like adhesives?
Yeah, so that was part of this research. So as I said, like combining that epoxy based adhesive so that it could actually form. If you don't go with that epoxy base, once you go to those higher temperature ranges, it doesn't bond as well. So you're kind of in a trade-off between the shear strength to that heat. So you're kind of losing one or the other. And in our problem statement and objectives, we kind of said that first we want to deal with actually maintaining the actual load cases. And then one of those objectives would be that would meet the load case of the temperature.
And then the other question is, you guys use like ANSYS for most of this, right?
Yes.
Did you do any vibrational analysis? Just because it just fitting at like 2200 RPM. And I know that we kind of have questions concerning the vibration of the engine mount in the current like steel design. And I don't know what the like frequency range for like carbon fiber is, but or the epoxy, but do you know if that would like be a concern?
We just due to the time constraint on this project, we did not really have time to do a vibration analysis, just because kind of how complex that can get. So I do not have a good estimate on that.
Yeah, I was telling these guys to focus mainly on the structure. We understand that the thermal is going to be a big headache, and we'll tackle that. You know, when there's other ways we can do, we can tackle that thermal problem. But if it's feasible structurally, then we want to move on with we'll do the thermal analysis.
Okay, well, that answers some of my questions. I'm a thermal guy and my questions were thermal. I mean, if you're talking about high temperatures and how do you manage that in terms of the strength, but if that was not their focus, then I
No,
understand.
that's really their focus. I'm glad, I mean, they investigated it.
Yeah.
Thank you for doing that, but I wasn't really.
At least identified it as an
Yeah.
issue.
And we understand it's gonna be an issue, but let's even see if it's feasible structurally.
Other questions?
Oh, I don't want to cut anyone.
Jose, go ahead.
Oh, please do.
Just wondering on the current job, by the way, I know this is, a lot of things are very weird. When you're gonna do the analysis of the composites, you're gonna do that analysis. What's gonna be kind of your approach to doing that? Because it can be so complicated to do. Kind of, are you gonna set some conditions and some boundaries and
Yeah, sure. So I'm pretty comfortable with ACP as far as setting up the material itself and its fiber direction and orientation and stuff like that. For all the validation that I did, I just applied them to the line of like the midplane of a laminate. However, in reality, in our truss, that's not how the line's going to be applied. So when I will go through and do the failure analysis, I will cut like kind of planes off in the section. And then on those surfaces where the adhesion is going to be at, those are where I'm going to apply my fixed supports and my forces. And then we'll look at the failure criteria from there.
Everything you've done so far with failure has just been like the amount of script, yes?
Yeah, everything in this presentation was all based off of classical lamination theory that I calculated using a math.
No failure yet in FEA.
No.
But that's coming.
Yep. First thing.
Other questions? Did you have?
I realized it was a thermal question.
Thermal questions, all right.
are there any considerations of mining strengths and all?
Well, lightning strike would have to go through the firewall, I mean, go through the cowling before we ever hit this. So the spinner would be a candidate, but I don't do much with part 23, so I really can't answer that question, so. But if you're flying that plane into lightning, that's something you probably don't want to do to start with,
I agree. All right, any from students or I'm all good, guys? Okay, well, if that's it, let's thank this group one more time. All right, that concludes the session. We're gonna short break until 10:30 and we'll resume talks at 10:30. Okay. Yeah.